Hi, everybody. We're going to talk about how to build or draw fragments from NMR data. And this is kind of really the accumulation of all of the past videos that we've been going through, talking about equivalent proton and carbon environment, the chemical shift, the integration, the multiplicity, all of that kind of coming up to how do we find structures from NMR when we're given them. So most of the fragments are going to come from the proton NMR data. Okay, so a lot of, and you've probably seen it already, a lot of the videos that we've been, where we've been discussing NMR have been focusing on that proton NMR because it's giving us the multiplicity, the integration. The carbon NMR is just giving us the chemical shift. What that chemical shift can do, though, is it really can be helpful in identifying our functional groups. And that's going to be in the proton and the carbon. Okay, so between using the IR, the carbon, and the proton NMR, you should have a pretty good idea of what functional groups you're working with and what kind of environment is going on around the various peaks that you're working with. So don't ignore that carbon NMR. It is very helpful. It also is helpful in kind of counting out those peaks and figuring out if you have symmetry likely, which we'll see when we go into the unknown video. Okay, so again, as we've kind of been seeing throughout this whole series, we've been looking at the NMR summaries, typically for proton NMR, where you'd have your chemical shift number, and then that would be followed by a multiplicity and an integration. Okay, so when we're taking all of this data and breaking it down into pieces, what that's giving us is it's giving us, again, information about that functional group or functional groups that might be involved. Okay, we're also looking at what kind of proton neighbors we've got. So what's going on next to that proton environment. So if we're looking at our neighbors, we got this one and we're saying what's happening around it. And that will help us start to build things up. So if we can think about that multiplicity as being, okay, it's next to a CH3 because it's a quartet. So I've got 3 plus 1. Okay, having that idea of what's next to it helps you build up those fragments. In the integration, that's telling you how many protons are in that specific environment. So that's really telling you, do you have a CH, a CH2, or a CH3? Or a multiple of one of those. So maybe do you have 2 CH2s that are in the same environment? Okay, that's going to be really important here, and that's what's going to allow us to actually start to draw things from these structures. So let's look at a few examples here, and keep in mind that these are just some examples that I put together just off of the top of my brain here. So I'm trying to get through most of the common fragments that you're gonna see, but keep in mind that there are gonna be, unique situations, different variables and factors and whatnot. So there's definitely things to be thinking about here. I'm also going to be using what I have in terms of chemical shift out of my head. If you're using the tables for this, definitely that is totally fine. And if you're using this video as a practice, I would recommend getting your spectral reference tables out now because they will help you just trying to identify what kind of areas our chemical shifts are in. But just to avoid a lot of flipping back and forth, I'm going to just do it based on what I know. Okay, so if I've got a chemical shift about 2.12, the first thing you're going to want to do is go look at that reference table and see what kind of area that shift lies in. Keep in mind that you want to really be accounting for the approximate nature of those values. If you have, a lot of electron withdrawing groups nearby, it's going to start shifting it possibly downfield outside of the box that is provided. So a little bit of wiggle room on all of those, I think is wise, just to account for any discrepancies in terms of, stacking up a lot of electron withdrawing groups nearby and kind of really having a de-shielding effect going on. Or even just the sum of 2 effects, like you've got an oxygen and a carbonyl nearby, those 2 effects are going to be having a summative effect rather than just kind of one or the other taking control. So 2.12, that's going to be in my alpha 2 carbonyl benzylic type region. Where should I put this? Okay, the alpha to CO, benzylic, allylic, that type of area. My integration is 3. So that's telling me as soon as I see an integration of 3, I'm immediately going to go to, it's probably a CH3. And this is when we really need to be careful about looking for horses and not zebras, right? There are situations that are fairly few and far between where like a 3 is not a 3, it's not a methyl, but it's actually a 2 and a 1 that are overlapping in some horrific way. Um, you want to look for the horses first, and if that's not working, if you're finding you're running into roadblocks, that's when you need to turn around and start looking for zebras. But most of the time, an integration of 3, I would immediately think of as that's probably a CH3. Okay, it's probably a methyl group. And a multiplicity of a singlet means that I have 0 neighbors. So I'm looking at some sort of methyl group that's maybe next to a benzene. Just trying to draw this in a way that's legible. Okay, so maybe it's benzylic, maybe it's next to a carbonyl. Okay, maybe it's next to an alkene, but that alkene couldn't have any neighboring protons on it. So we could have fragments that look like that. Okay. So when you're drawing your fragments, I'm obviously going a lot broader here because I don't have any other context. But when you are doing this on an NMR, you will have the context of things like the IR and the carbon NMR, probably the molecular formula. All of those are going to help give you a little bit of context to kind of narrow this down. So for instance, if I had evidence of a carbonyl in my carbon NMR and in my IR, I'd probably be tending towards the alpha to carbonyl situation. Okay. If I had evidence of a benzene in my carbon NMR or my IR, maybe I'd be going more towards that benzylic situation. So the context there is going to be really helpful. All right, so 7.3 chemical shift. As soon as I see that, I'm really thinking aromatic region. And especially if I've got an integration of 5, okay? Benzene has 6 H's. So anything that's like 5 H's or less, I'm thinking benzene, and especially in that chemical shift region. You will frequently see aromatic peaks that are going to be overlapping each other. So integration of 5 and then a multiplet is definitely saying, yeah, I've got, different environments in this benzene ring, but they're all kind of overlapping on each other and forming a mess. So the number of neighbors, who knows? It's unclear, right? That's what a multiplet gives us. It is unclear. But what it does tell us is as soon as I have that piece, I know that I have that fragment that I need to add in somewhere, okay? Because this has 1, 2, 3, 4, 5 protons on it. I would expect to have a lot of kind of peak overlap with these aromatic protons. It is aromatic, and then I just need to find something to connect it to. And typically when I'm drawing out these fragments, I use that wiggly line to indicate like this has to be connected somewhere else because we don't want to be drawing full-fledged molecules at this stage. We want to be drawing pieces of molecules based on what this data is telling us. Okay. If I've got an integration of 2, again, I'm looking for horses here. I'm going to probably be thinking about a CH2. CH2 that has a chemical shift of 4.05, that's in the alpha to electronegative atom region, so alpha to O, N, X, that kind of thing. And it's a quartet. So if it's a quartet, that means it has 3 neighboring hydrogens. If we're thinking about N+1, we're basically taking away the +1. So we're back down to 3. So we can think about that as being next to a methyl. Okay, so it's a CH2 next to a CH3. And then that starts giving us a really nice fragment. It also gives us an end point, like a terminal, right? That terminal is our methyl group because that can only be attached on one side. It can't be attached anywhere else. So what this gives us is we know that we've got our CH2 here, and this is the thing that's actually creating the peak next to a CH3 that is connected to some kind of electronegative atom that is connected to something, possibly. Okay, so that's helping us get a lot of information here out of that very small little line of data. Okay, next one, 1.3. So that is just pretty much alkyl region. So not nearby anything in particular. The integration is 3. Again, I'm going to be thinking CH3. If I've got a multiplicity of triplet, then that means I've got 2 neighboring hydrogens. So we're probably next to CH2. Okay, so if I start putting all that together, I'm looking at a CH3 as my main peak component next to a CH2. And again, we're looking at these 3 H's right there. And I don't really know what's happening on the other side of that. But what that does tell us is we can see that when we have these two together, we're seeing that we've got some overlap here where this CH3 could be that CH3, right? So the ethyl group that I drew here could be showing up as another fragment somewhere else in your spectrum. And again, keeping in mind, none of these are actually going together into one single thing. It's mostly just kind of single fragments that I'm looking at here. And again, that context is really important. Okay, so chemical shift of 1.1, we're again looking at alkyl. If my integration is 2, I'm going to be thinking CH2. And I've got a quintet, so which is five little tips. So that means I've got 4 neighboring protons. So if we think about how to get 4 neighboring protons, there's 2 options. You can either be next to a CH and a CH3 or 2 CH2s, okay? And this is something like maybe it would make sense to not be discounting either side of that at this stage. Okay, where we have those 2 peaks actually showing us the 1.1 chemical shift peak. And then another option that you could be thinking about here would be something like this fragment, okay, where I've got a CH3 on one side, I've got an H on the other side, and then I've got some connections to something. I don't know what it is, but it might be in that kind of more branch style versus chain-like, okay. 3.9, an integration of 1. So 3.9 is again kind of in that alpha to electronegative atom area. Okay, and an integration of 1 makes me just think CH. Okay, so you can just start off thinking like, okay, I'm going to start drawing a CH and then add on to that. If it helps too, you can do exactly that and just be thinking about the fact that with the integration part, I can't be putting more H's on that carbon. I probably have something electronegative on that carbon. Hold on a second. Let me think about this. Just making sure that I have this in the Need to pause and think. Okay, had my little think and I realized what went wrong here. So the reason that I got stumbling there. So I was looking at the nonet. Okay, a nonet is going to be nine neighbors, or 9 little peaks. So that means I've got 8 neighbors. There's no way to get to 8 while also being alpha to an electronegative atom because there's just not going to be space on that carbon. So what we're going to do is we're going to change this to 1.6 and stick it in the alkyl region. And then it's going to make sense. Okay. So when we're looking at 8 neighbors, if we kind of think about using our general working pieces of CH, CH2, CH3, we can get to that non-et with 2 CH3s and 1 CH2. Oops. Okay, so again, we have the 1H, and then we can think about that electronegative atom is not going to be there. So we can have a CH3, a CH3, and then a CH2, and then something connected on the other side, okay? Where again, that H is the one that's actually giving us that 1.6 peak. And now we've got the 8 total neighboring protons. Okay. I put together one that was impossible because I was just in a rush. All right, so if we're looking something like 0.8 ppm and 9 hydrogens and a singlet, okay, whenever I see 9, you always want to be thinking about what is a number of CH, CH2, CH3 that I could get in that, and have it obviously be still all the same environment, especially because it's showing up as a singlet. So that I always just think of 3 CH3s. Okay, 3 times 3 is 9. If it's a singlet, I've got no neighbors, so it's not going to have any neighboring protons. And this one is really distinctive because the best way to get 3 methyls in the same environment is to put them on the same carbon, okay? And that's going to be typical of a lot of these. Having them in the same environment often means on the same carbon. Okay, so that's pretty indicative of a terbutyl group. The next one, 1.2 and integrating to 6. So 1.2 is again our alkyl region. Okay, and integrating to 6, probably going to be 2 CH3s. Okay, it would definitely be zebra territory to be having it as the 3 CH2s. That would be kind of a lot to be dealing with. So 2 CH3s, and if it's a doublet, we've got 1 neighbor. So it's going to be next to a CH. So if I've got 2 CH3s in the same environment, again, I kind of want to be thinking about like, let's just put them on the same carbon. And then I know that I need to have 1 neighboring hydrogen, and I still have another connection on that carbon that I'm going to need to deal with. Okay, and then I've got my 2 CH3s integrating to 6. We've got 1 neighbor for both of them, and then it's connected to something else. And then finally, 7.4. So again, I'm back in that aromatic region. If I'm integrating to 2, I've got 2 H's that are in the same place. Now, on a benzene ring, I know that I can't have them both on the same carbon because each carbon only has a max of 1 based on the double bonds. So we want to keep that in mind, that 2 here is definitely 2 CH's. Okay, because we're thinking about benzene where we only have 1 H per carbon. Okay, if they are doublets, that means that they've got 1 neighbor. So it's next to a CH. Okay, but importantly, only one CH. So think about when you're having, depending on how you set up this benzene ring, okay, I need to have an H there, and I need to have two of them, and they need to be doublets. So I'm going to start off just putting them opposite each other. And then I could be thinking about something like that, right? Where I have that H and that H are going to be mirroring each other across this plane. And both of those have the one CH neighbor. So I could do something like that. I could also be looking at something like a para substitution, where again, I'm going to have the two H's that are closer to the X, and they both have the one neighboring proton there. So different options there. Benzene, I would say it definitely is going to take some practice just to kind of get used to some of those situations there. But very, very helpful to be able to build those fragments and just kind of start with this table to get yourself some stuff written down so that you can put the puzzle pieces together and start shuffling things around. Alrighty, so I will show you in the next video what to do with all of these, but it's going to be for an actual structure that is usable and you can actually put it together into one piece. All right, so let me know if you have any questions and I will see you guys all later.